Swayam Prabha. Digital India. Educated India.
Good morning. So, let us take a example on calculation of mutual inductance to begin with. So, let me start with a, let us say I have 3 mutually coupled inductors. Deliberately I am taking 3 of them, so that the problem becomes a slightly more tricky. And now what I want to do is, I have each of them has a inductance of, let us say, L henries, or let us say 2 henries, L henries. Let us keep it general. So, the each of these 3 inductances is of L henries each, and each of the mutual inductances is M henries. So, there is a mutual inductance here, there is a mutual inductance here, and there is a mutual inductance here. Let us say that M is L by 2. Let us further specify to make it more easy. Let us specify it to be M by 2. Now, let us look at the mutual coupling that we are having here. So, let us say that the mutual coupling is like this. So, let me just once check up. Yeah, so yes, so the mutual coupling is as follows. So, now my question is, sorry, this one is connected here, circuit is closed like this, and voltage source is connected somewhere here. This is the way a voltage source is connected here. So, I connect the voltage source. Sorry about that. So, the voltage source is connected like this, and the question is, what is the L equivalent. So, let us say that the current entering this terminal is I, and it splits into 2 components, I1 and I2 like this. So, I will mark the I1 component somewhere down below, it is easier like that, I1 and I2 like this, and we are defining V of t to be equal to L equivalent di by dt. Question is, what is the L equivalent? Now, let us, for the sake of simplicity, take M to be L to be equal to 2 henries, L to be equal to 2 henries, so that M will become equal to 1 henry, So, the M will become equal to 1 Henry and our calculations will be, so to say, simpler. So, I have I am going to take two loops. First of all, if you observe at this node, let me change the color. If you observe at this particular node, the blue one which I am marking here, if you observe at that, then the KCL says that I is equal to I1 plus I2. Is it not? That is the statement of the KCL. Now, first loop that I am going to take to write the KVL, the first loop that I am going to take is this particular loop, in which this is the loop 1, and in this loop 1 I am going to start from this particular source. So, the voltage rise V of t, will be written as equal to the voltage drop in the two inductors, this and this, the center limb and the left one. So, the first one will be, if you look at this figure, the first inductor, the voltage drop is going to be, let me move this figure a bit below, so it is easier to okay, can I paste it? Let me paste it up first. Yeah. So, if I look at the first inductor at the top, this, let us call this as voltage drop across this as VL1. The first, this, let me call this VL1, the plus and minus here, and let me call this as VL2 and let me call this as VL3. So, first let us, if you write the equation for the loop 1, you will get if you write the equation for the loop 1, you will get Vt to be equal to VL1 of t plus VL2 of t. So, let us write VL1 of t. VL1 of t is going to be equal to 2 times di by dt plus, this is the drop due to its own self inductance, and then we have to add drop due to this and due to this. So, inductor 2 and inductor 3. So, if you look at the mutual inductor 3, which I will first take the mutual inductor 3. So, the current entering the dotted terminal here is I2, and so the M di by dt, the drop that the voltage that it is going to induce will have a positive polarity here and a negative polarity here. So, therefore, I will get 1 times di3 by dt, 1 times di3 by dt as the voltage drop occurring across VL1 due to current I2 flowing in the inductor 3. Now, if you look at the inductor 2, the current I1 is flowing out of it. So, therefore, it can be treated as minus I1 entering the dotted terminal. So, therefore, it will create a voltage drop of mutual inductance will create a mutual drop of minus 1 dI 1 by dt. So, therefore, this can be written as 2 times dit by dt minus di1 by dt minus plus di2 by dt. Let us mark this as equation number. This is VL1. Now, let us take VL2 because V of t is equal to VL1 of t plus VL2 of t. So, therefore, now let us write the equation for VL2 of t. So, VL2 of t is going to be equal to first its own self inductance drop, which is 2 times d I1 by dt, and then due to mutual induction from inductor 1 there will be one drop which will be there, and due to mutual inductance from 3 there will be another drop which is coming here. So, now the current is going to, let us take for example the drop due to mutual inductance L1. So, the current is now entering L1, and then if the di by dt is positive, what it means is a positive voltage will come out here and a minus will come out here. So, it is going to be a voltage, rise. So, the voltage rise has a subtractive polarity. So, therefore, di by dt, therefore, minus of di by dt, and again here the current I2 is entering the inductor L3. So, therefore, again a voltage rise is going to come. So, again minus of di2 by dt. So, if you now add the two equations, what is it that you are going to get? You are going to get V of t to be equal to, so 1 di by dt will cancel here. So, I will get di by dt, then 1 di1 by dt will cancel here. So, I will get di1 by dt, and the I2 di2 by dt will cancel with this I2 di by dt. So, therefore, nothing is going to come from I2 di2 by dt. So, therefore, this is all that I am going to get. Now, you may wonder why di2 by dt has not come into picture. So, conceptually if you look at it, see the mutual inductances are all same. So, it induces 1 di2 by dt drop in this, which is a drop actually, mutual inductance is drop because current I2 is entering here. So, plus and minus will come here and it will be a drop. But the same 1 di2 by dt is also induced due to induction in this inductor, but here it comes as rise. So, when I traverse the loop, once the same mutual induction drop comes as actually a drop, and once it comes as a rise. So, it cancels out and I get V by 2 equal to di by dt plus di1 by dt. So, let me call this as equation number 1. Now, the other loop that I am going to take is the outer loop, is this particular loop that I am going to, this is the loop which I am going to take now. and in this loop, what is the equation that I will write? V of t equal to VL1 of t plus VL3 of t. So, the equation that I am going to write is this voltage rise V of t is equal to drop in this plus the drop in this, and VL1 of t anyway I have already written. So, I do not have to write it again. So, only thing that I need to write is VL3, and so let us write the VL3. I will first write it here and then copy paste it downwards. VL3 is going to be its own self inductance drop, which is 2 di2 by dt. Write it here, 2 di2 by dt, and then the mutual inductance drop due to inductor L1 and mutual inductance drop, voltage drop due to inductor L2. So, if I take due to L1, mutual inductance is 1, current I is entering the dotted terminal, it creates a plus voltage, induces a plus volatility here, plus and minus polarities here. So, it comes as a drop. So, I will write it as 1 times of di by dt, and here in the second inductor the current I1 is leaving the dotted terminal. So, 1 di1 by dt will come again, will come now as a voltage rise, because current leaving the inductor is I1. So, current entering this dotted terminal is minus I1. So, if you look with plus and minus as the convention, the voltage induced is 1 times minus di1 by dt. So, it will be minus 1 times of di1 by dt. So, let us take it down. And what we have got now is equation for VL3 of t. So, therefore, now we can write VL1, so we can substitute for VL1, this is the substitution for VL1, plus substitution for VL3, and if you add them together, let us see what do we get. So, these ones need not be written down now. So, we will get 2 di by dt plus 1 di by dt will give you 3 di by dt, then minus di1 by dt minus di1 by dt will give you minus 2 di1 by dt, and di2 by dt plus 2 di2 by dt will give me 3 di2 by dt. So, I have this as the second equation for V2. Now, in the first equation I have only I and I1. So, it is better if I only have I and I1 as the variable in the second equation also. So, to that end, what I will do is I will write the Kirchhoff's current equation, use Kirchhoff's current equation to eliminate one of these two currents. So, I is equal to I1 plus I2. So, because I is equal to I1 plus I2. So, I will get this as 3 di by dt 3 di by dt, substituting in the I2 equation 3 times of d by dt of I minus of I1, which will make it 6 di by dt, 6 di by dt minus 5 times of di1 by dt. So, let us call this as equation number 2. So, now we can actually equate 1 and 2. So, this is the equation number 1, and if you equate 1 and 2, you will get relationship between I and I1, which can be that 6 di by dt minus 5 di1 by dt is equal to di by dt plus of di1 by dt. So, 5 times of di by dt is equal to 6 times of di1 by dt. And now, if I substitute this in equation number 1, this one, the third set of equation here, if I substitute in equation number 1, because finally I want a relationship between V, the voltage which is applied, and the current I which is pushed in the circuit. So, therefore, if I do that, then I will get that V of t to be equal to di by dt plus di1 by dt can be written as 5 by 6 of di by dt. This is going to turn out to be 6 plus 5, 11 by 6 di by dt. So, therefore, V of t by di by dt, which is equal to the L equivalent, this is the V of t, this is the I, and this is the L equivalent, is going to be equal to 11 by 6 Henry. So, this is under the condition that L is equal to 2 Henry and M is equal to 1 Henry. Suppose L was 1 Henry and M was half Henry, then everything being half, the L equivalent would turn out to be half of this value 11 by 6, which will be 11 by 12 Henry, and hence if all the inductances were L and all the mutual inductances were L by 2, then the L equivalent will turn out to be 11 by 12 into H Henries. So, this is going to be my mutual inductance of this coupled circuit. So, you can see here how I have used the dot convention to properly write the voltage drop equations across each of the mutually coupled inductors, and it is okay if I have 2 or more mutually coupled inductors, it is absolutely fine. I have to just, it becomes a bit more tedious to write the equations, yet I could finally simplify everything and get one final answer for the equivalent inductance. So, this is a good example, it shows that such circuits can be simplified a lot. Now, let us take one more example. The example that I am having now is that I have in the figure shown below, the 4 windings are there, 1, 2, 3, 4, 4 windings are there. Or let me make my own problem, no problem, let me make my own problem. Let us say I have three mutually coupled coils. Okay. Let us say this coil is wound like this, and this coil is wound the other way. And this coil is wound again in this particular way. This is coil 1, this is coil 2, and this is the coil 3. Now, let us say by my convention current I1 enters here, current I2 enters here, and current I3 enters here. So, what I want you to do now is to, because the orientation of the windings is given, the how they are wound up, that is given here. So, what I want you to do is put appropriate dots on the mutually coupled coils. So, this is what I want you to do. So let us say that first of all, let us start with the first coil. The current is entering the coil is I1. So, let me first of all put a dot here. First dot I can put randomly, right. So, I will assume that since the current is entering the coil 1 is I1, I have put a dot here. Now, what do I say? It will create a flux path in the arrow direction shown. So, now we will evaluate if the current is entering the terminal I2, okay, if the current is entering I2 like this, in which direction does it create the flux? So, it creates a flux. If you take a right handed screw and rotate, it creates flux in the upward direction here. So, I will change the, just put a green here, and it will create a flux in this direction, which will go in this direction, will come down in this, go like this, come down like this, and circle back like this. So, the way it is pushing the flux is non-additive way, it is non-additive way. So, I cannot put a red dot here, I should put the red dot on the other end. And if I put the red dot in the other end, and if you take a current which is entering that red dot and move a right handed screw, you will see that it is coming back, that is, it is creating a it is creating a flux direction which is in same orientation to as the current which is entering I1. So, I have put the first two red dots. Now, the third red dot I have to put for the winding number 3. So, the third red dot I have to put for the winding number 3. So, if the current enters from the top end the winding number 3, then the flux that it will create is, if you rotate this right handed screw, you can see that it is moving towards the camera, or in other words it is creating let me use another current. It is going to create a flux like this, which will then of course go and break in the other way. So, it opposes the flux which is created by I1. So, therefore, it opposes the flux which is created by I1. So, therefore, the dot has to come on the other side. So, if the current enters the winding 3 from the lower end, it will create a additive mutual coupled flux between the two windings, and therefore, the two dots will come like this. So, we have put the 3. So, we have solved 1 to 2, 1 to 2, 1 to 3. We have solved both these dots we have put for this. The last set of dots that I would like to put, though there are already 2 dots, so you can infer something from there, but instead I am going to put one more set of dots which is for 2 to 3, how the flux should be taken if it goes from 2 to 3. So, let us see. The current enters let me put the current enters I2. It is always current, first dot should be put where the current is entering the first one coil. The I2, at the I2 where it is entering, I will put the first blue dot there. Now, once I have put the blue dot there, I can evaluate where this flux is, in which way the flux is going to come. So, it is going to move the right handed screw in my direction. So, therefore, it is going to create a flux in this direction. So, therefore, when it goes here, it is going to be in this particular direction. And now, if the current enters is entering, if the I3 current is entering, then the right handed screw moves in your direction. So, therefore, it also creates a flux, which is in your own in the same direction as the blue flux. So, therefore, it is additive, and so therefore, what I will do is I will put a blue dot here also. So, once I have put this blue dot, then you can easily check that these blue dots are right. So, now I will rub all this unnecessary flux paths that I have put here, and I come to the conclusion. I come to the conclusion that these 3 coils out from outside, whichever way you want to connect it, you can connect it afterwards, but these can be shown like dots. This is I1, this is I2, this is I3, then the first red dot is here, the second red dot is here, the third red dot is here, and the two blue dots are here and here. So now all the polarities from 1 to 2, 1 to 3, 2 to 3, because 1 to 2 is done, then 2 to 1 is also done. So that is why I do not have to redo 2 to 1. So only 2 to 3 is required, and then 3 I do not have to do any separate exercise, because 1 to 3 is already done and 2 to 3 has also already been done. So this is the dot polarity. Once these dots are given to you, then once these dots are given to you, you do not need any specific orientation like this. That is the reason why we use dot convention. Now let us look at these were two nice and simple examples. Now let us look at energy stored in an inductor, and I will keep just as a background, I will keep a simple geography circuit like this in mind, but whatever I am doing actually is quite generic. It is not very specific to this particular geometry, but so the length of the magnetic path is L, area of cross section is A. So what I am going to do now, first of all, we apply, it has an inductance L, and we apply a voltage source V of t, and we want to now find out, it pushes a current I initially de-energized. So you could even think of a switch somewhere here, and the switch is closed at t equal to 0, and the question asked is, if the current is I of t, what is the energy stored at I of t in the inductor. Inductors and capacitors are storage elements for energy. Resistor is a dissipative energy element for energy, the circuit elements. So we know that V equal to L di by dt, which is also same as V d psi by dt, the flux linkages, which is equal to product of L times of I. So instantaneous power P of t is V of t into I of t, which is nothing but I times of d lambda by dt. So P dt into dt will be the energy which is pumped into the inductor. So therefore I can write dE as equal to I times of d lambda, but lambda I can write it as n times of phi. So therefore I can write it as I into n times of d phi, which is n times of I, and then the d phi I can write it as b phi, I can write it as b times of A. So therefore I can write this as A times of dB, d phi can be written as A times of dB, but the MMF Ni can be written as H times of L, and therefore this can be written as H times of L into A into dB, and all of this unit is joules. So if you look at this, L times of A, that is the volume of the iron here, area of cross section is A, and the length of the magnetic, average length of the magnetic circuit is L. So, therefore, L times of A is basically L times of A is basically the volume of it. So, if I divide dE by L times of A, then it becomes H dB, whose unit is joules per meter cube. So, therefore, one thing which which I have brought out from here is that energy stored, if you change the magnetic field intensity by dB, then and the flux density by dB and the magnetic field intensity or ampere turns is H, the per meter is H, then an amount of per unit volume, the amount of energy which will be pushed in our storage element will be H times of dB. Let me come back to this equation. This is a more convenient form for manipulating the circuits. So, V is equal to L di by dt. V times of I, the instantaneous power, is Li di by dt. Vi dt is the instantaneous energy which is pumped in, is therefore equal to Li di. And so, if the in time t the energy which will be pumped will be this integration of dE, which is same as integrating from 0 to t Li di, and initial condition when the switch is open, and I am treating this inductance as a linear element here. Please note that L is a constant in this discussion. So, then this will be same as L times integral 0 to t in time t, the current will reach to I value, I times of di, and this is nothing but half of Li square. So, therefore, the energy stored in a fixed constant inductance I, which is initially de-energized, and then when the current reaches a level I in it, then the energy which is stored in the inductor is half Li square joules. Now, this can be written, this can be manipulated in many forms, but before I do get into that, let me first discuss one quickly an important thing, which is that if I had mutually coupled coils like this, right, and this was L1, L2 and M, then we had said that L equivalent is L1 plus L2 plus 2M. So, now this is as good as saying that I have a L equivalent and a V of t is applied here and a current of I of t goes in here. So, now I can very quickly answer the question, what is going to be the stored energy in a mutually coupled coil also. So, the stored magnetic energy E is going to be at time t is going to be equal to half of L equivalent I square. So, therefore, if I substitute for L equivalent, half of L1 plus L2 plus of 2m of I square, which is half of L1 I1 square plus half of L2 I2 square plus half of L1 I square plus half of L2 I square plus mi square. In general, this tells you that in general for a mutual coupled coil, if they were carrying current I1 and I2 separately, I could have derived energy stored as plus m times of I1 I2. I leave it to you to think it over. And if the polarities convention were like this, then instead of it coming with a plus sign here, the mutual inductance would then become L1 plus L2 minus 2m. So, therefore, it will come with a minus sign here, a minus sign here, and therefore, a minus sign here. So, therefore, in general this can be written as plus minus m I1 I2. So, this is how we can actually calculate the energy stored not only in the coil which is having only one not only in one single inductance, but also in mutually coupled coils. And if you want, you can write it as M12 not required, then you can write this equation as follows. So, the energy which is stored in a mutually coupled coil is not just the energy which was half Li square from the first coil plus half Li square from the second coil, but rather there is one additional component which is m I1 I2. Now, let us come back, and of course, the unit is joules. Now, let us come back to the hysteresis circuit that we had discussed earlier, if you remember, and it is not come out that very well. This is much better. I want to know in this circuit, I want to find out when it goes through us, when this magnetic material is subjected to alternating voltage source, and therefore, the current alternates in it, and when the current alternates in it, the flux density flux alternates in it. So, the B alternates in it. So, therefore, we had discussed earlier that the grains, suppose if it has been repeating for a long time, then it will settle down to a hysteresis cycle like this. So, what will happen, let us say we start from here. So, this is the we start from this particular point where the B is 0, and to get that B 0 we have applied a current I. This is the remnant B in it, once positive, once negative, and these are the coercive forces which are used to cancel whatever is the existing B, which here was negative. So, the dipoles were aligned in opposite way, magnetic dipoles were aligned in opposite way. So, we applied positive current to it, and gradually they got de-aligned and became random, after which they started realigning and increasing the B and so on. So, we have understood this earlier also. Now, what I want to show to you is, when a ferromagnetic material like this, it undergoes a hysteresis cycle like this, it is going to lose energy. It is going to lose energy, means what I mean to say is, heat energy will be produced when it goes through the hysteresis, and this heat energy has to come from where? It has to be provided by the voltage source. So, there is a loss, hysteresis loss or dissipation, which is due to friction faced by the which is due to the friction which is faced by the magnetic dipoles. And we want to find out what is this loss in joules per cycle. So, that is our question, what is the loss in the joules per cycle. So, one cycle, if it creates, let us say 5 joules of loss, then 50 cycles like what we have for a 50 hertz system will create 250 joules of loss per second, which will mean 250 watts of which will mean 250 watts of loss in the magnetic material due to hysteresis. So, to calculate it, let us come back to this equation that I had derived. This. This is the this is the energy, the differential energy dE is h times of dB joules energy stored when I increment, I am at some level h, okay. I am at some level h here, I am at some level h here, and I increment the, so the B is somewhere here, and I increment it B by dB value. So, I increment the B by a dB value, then what is going to happen is h times of dB. So, this small strip which I am having here, this small strip that I am having here, this is the h dB. So, this small strip that I am having here, this is nothing but the h dB which is taking place, this is the dB, and this is the energy which is stored when the B is incremented by dB value. So, if I start from 0 and do this activity, then you would agree with me that the energy which is going to be stored, which is going to be filled up, is going to be something like this. It's been a bit too thick right now, but I let me see if I can make it thinner. Yeah. So, this is what is going to, this area will represent the joules per cubic meter amount of energy which is stored in this magnetic material. But when it starts going through the other cycle here, when the current starts reducing, because the current has to increase, then come back to 0, then go back to the negative maximum, then increase back to the positive maximum. So, when the current starts decreasing like this, then what it will start doing is, it will start returning back the energy to the source. So, it will start returning back the energy to the source, and what is the energy that it will return back to the source? Again h times of dB, but now where is the h to be plotted? For example, if h is here and it reduces the dB by a small amount, then it is this particular strip where it is returning the energy. So, what you can see is basically this outside area, this outside area, this is the area which is energy in this, whatever is represented by this area, this energy is reduced. So, is returned back. So, at the end of the day, I am sorry. So, at the end of the day, what is going to happen is, what is the, when you go through the complete cycle, what will be left is only this much. This is all the area which is enclosed is what will be left as the residue, and that is this area. Therefore, inside the hysteresis loop represents the joules per cubic meter lost in one cycle. This loss is a heat loss. So, you have to the source is providing it. So, the energy which is lost, the hysteresis loss per cycle is going to be h dB of this value, and usually this is proportional to some b to the power x, like x could be for example 1.3 or 1.4 or something like that. And then if f is the frequency of the supply, so then it will be increased. It is this is joules. This is joules per cubic meter per cycle. So, therefore, if you want to see the hysteresis loss, if the frequency is f, it should be further multiplied by f, and if the volume is V, then it should be further multiplied by V, and then there is one constant Kf which can be put in place, and then this will become the in watts. Now, everything is watts because per second, the net loss, net hysteresis loss of magnetic circuit. We will stop here for now. Thank you.